Evening everyone. Am I audible? Am I audible? Good evening. Welcome to Goscore Learning, the fastest growing edtech industry in the Middle East. We are here to make your learning easy. I am Dhanya Rakesh, teacher from the Department of Chemistry, Goscore Learning. Today I am here with the third part of your Chemical Kinetics chapter. In the first and second part, we have already completed the rate equations as well as the order, rate of reactions, the molecularity of reactions and everything we covered. And today we are going to discuss about the effect of temperature, catalyst on the rate of the reaction as well as about the collision theory. Okay, and I have included some important questions that asked for the previous year question paper for your practice session. Okay, so are you all ready? Can we start the session? Okay, so first we can discuss about the effect of temperature on the reaction rate or the rate constant. Okay, we all know that whenever you increase the temperature, how the reaction will proceed? Will it proceed in a faster way or will it proceed in a slower way? If you take a cold water and you take a hot water, if you want to dissolve a sugar or salt in that, which one will dissolve in faster way? Because the sugar will dissolve in a faster way in the hot water, right? Because whenever there is an increase in the temperature, the rate of the reaction also increases. Okay? If your rate of reaction, when the temperature is T, the rate of reaction K will be rate constant is equal to K. When you increase the temperature by 10 degrees Celsius, you can see that the rate constant get doubled. That much faster way the reaction will proceed. Okay. So, whenever there is an increase in the temperature by 10 degrees Celsius, you can see that the rate constant get nearly doubled. Okay. So, the relationship between the effect of temperature on the rate constant is given by Arrhenius equation, which is a very important equation in this chapter. Okay. Now, let's see what is Arrhenius equation. According to Arrhenius equation, the rate constant K is equal to A into e raised to minus A by RT. Then what is this K? That is the rate constant, right? Then what is this term A? A is nothing but the Arrhenius factor, okay, or the frequency factor. Arrhenius constant or frequency factor is the letter A. It will be usually a constant for a specific type of a reaction. Okay. And then what is this EA? E with subscript A, that is activation energy. Okay. EA is nothing but activation energy. So, do you know what is activation energy? Activation energy actually we will discuss in detail in the catalyst session, but for your understanding I am telling activation energy for certain reactions to take place, the reactant molecule should possess some extra energy that lead to the collision of the reactant molecule and thereby lead to the formation of product. Okay, and that extra energy that is possessed by the reactant molecule is what we called activation energy. We will discuss about it detail. Okay. Now see what is this R. R is nothing but the gas constant and the value for R is 8.314 joule per mole Kelvin. Okay. This value you should remember because this will be used in the solving of problems. Okay. So the value of R is 8.314 joule per mole Kelvin. Okay, then what is the T? T is nothing but temperature in Kelvin scale. Okay, so this is a very important equation, that is the effect of temperature on the rate constant is given by Arrhenius equation, and the equation is K is equal to A into e the power minus EA by RT. In that, K is the rate constant, A is the Arrhenius constant, and EA is the activation energy, R is the gas constant, and T is the temperature. Okay. Now let's see, for a particular reaction, here we are taking hydrogen combining with iodine to give hydrogen iodide molecule. Okay, see here we can write the hydrogen as like this. That is the two hydrogen atoms combining and giving the hydrogen molecule. That is combining with iodine. Okay, I2. Okay, so when these two reactants combines, there will be a formation of an intermediate complex or an activated complex. Let's see what is the structure of that intermediate complex. It will be hydrogen, hydrogen, iodine, iodine. This hydrogen and iodine will form a temporary like this. This is what we called intermediate. Okay? Intermediate or activated complex. This intermediate is very unstable, so it will suddenly break down to give the product. Okay, so it will be breaking down to give hydrogen iodide plus hydrogen iodide. This is what we represent here, 2 hydrogen iodide. Now see here, the reactant molecules combines to give an intermediate complex. So the energy required to produce this intermediate complex is what we called the activation energy. Right? So here during a reaction, the reactant molecules will collide with each other to form an intermediate complex, and the energy required for the formation of that intermediate complex is the activation energy that we are denoting by letter EA. Okay, and this intermediate is unstable in nature and it will be breaking down to give the product. Okay, so let's see. The energy required to form the intermediate is called the activation complex, is known as activation energy. That means for producing the activation energy or providing the intermediate complex, the reactant molecule should possess some extra energy. With that extra energy itself, the reactant molecule will collide with each other. With that collision, if it is an effective collision, then only the product will be forming through an intermediate complex. Okay, initially the reactant will react to give the intermediate complex, which will then converted into the product. Because of the instability or unstable, intermediate will suddenly changes to form the product. Okay, so here we can see, if you plot a graph of potential energy, if you plot a graph of potential energy versus the reaction coordinates, you can see that for the reactant molecules, that is for hydrogen and iodine, the potential energy will be lower. It will react to form the activated complex, and that energy required to convert the reactant into this activated complex is the activation energy. That difference in the energy between the reactant molecule as well as the activated complex is what we called the activation energy. Once this reactant attains this activation energy, then only the reaction will proceed to give the product, right? So we can see that the graph will be like this, and then it decreases to form the product. Here when you notice, you can see clearly that the potential energy of reactant is lesser than that of product. Okay. Now let's see how the temperature will affect the rate of the reaction. We have already mentioned that whenever there is a 10 degrees Celsius rise in the temperature, the rate of reaction or the rate constant will almost get doubled, right? So, increase in the temperature, it will cause the more number of fraction of molecules to attain the activation energy. See, increase in the temperature of substances increases the fraction of molecules which will collide with energies greater than activation energy. So, when there is a rise in the temperature, more molecule will get energy that is greater than the activation energy. So, they will start to collide with each other in a faster way. So, obviously, the rate of the reaction or the rate constant will also get doubled. Okay. See, when you are plotting a graph of fraction of molecules, that much how much molecules are having that activation energy against the kinetic energy, we can see that when the temperature is T, the curve will be like this, isn't it? When you increase the temperature, you can clearly see from the graph that the curve broadens. The curve broadens. That means more number of molecules or more fraction of molecules possess the activation energy or greater energy greater than activation energy, right? So, there will be more number of reactant molecules colliding in a faster way. So, obviously what will happen? The rate of the reaction will also get increased. Okay. So, what happens when you increase the temperature? The more fraction of molecule will attain the energy that is equal to or greater than the activation energy. So, the reaction will proceed in a faster way and of course, the rate constant will get doubled. Okay. Now, I hope the effect of temperature is clear for you. Right. Now, let's see how we can plot the graph based on the Arrhenius equation. Okay, what is our Arrhenius equation? What is the equation? It is K is equal to Arrhenius factor A into E the power minus EA by RT. In that, EA is the activation energy, R is the gas constant and T is the temperature in Kelvin, right? So, when you take the natural log on both sides of this equation, how can we write? It will be ln K is equal to ln A into e raised to minus EA by RT, right? Send it. So, this one we can rewrite it as ln K is equal to ln A plus ln e raised to minus EA by T, isn't it? So, this one I can rewrite it as, in the last second part of the video we have discussed that log A raised to power B. What it is? It is B into log A. Same like natural log, ln A with power B is B into ln A. Okay. So, how we can rewrite this? It will be ln K is equal to ln A plus, what is this? Minus EA by RT, EA by RT, ln E. ln E is 1. Okay. It here E is equal to ln E is 1. So, how we can write it? ln A is equal to A minus A by T. Got it? So, if if I am just rearranging this equation, how can I write? It will be ln k is equal to, I am taking this EA on this side, that is minus EA by R into 1 by T. I can write it like this, right? EA by R into 1 by T plus what? ln A. Now see, what is this equation? It is in the form of y is equal to mx plus c, right? So if you take ln k on the y-axis and 1 by t on x-axis, what will be you are getting? Your slope will be minus EA by R, right? So how we can draw it? It is a minus slope, then it will be line like this, isn't it? The same thing we have discussed for differential rate equation. We have plotted the graph for zero order reaction, first order reaction by getting this straight line equation. I hope you all remember it. So here, when we plot the ln k, natural log of rate constant, against 1 by t, we will be getting a straight line with negative slope, that is minus EA by R. Okay, and if you extrapolate this graph to y-axis, what will be the y-intercept we are getting? It will be natural log of this factor. Okay, now see one more thing, just listen here. We got the equation like this, ln k is equal to what? Minus EA by RT plus ln A, right? This is a natural logarithm. If you convert it into log, what we will get? It will be log k. How we will convert natural log into log? You remember it? ln A we can convert into natural log by multiplying with 2.303. So ln A is equal to 2.303 into log A, right? So when we convert this, we will be getting 2.303 into log K equal to minus EA by RT plus 2.303 log A, right? So when you take this two terms on the right side, what we will get? See, it will be 2.303 into log K. I am taking this on the right side. Then it will be log K minus log A, right? So this is equal to minus A by RT. Okay, so I can rearrange this equation as log A minus log A is equal to minus EA by this 2.303 will be coming to right side, then it will be divided by 2.303, right? Then it will be 2.303 RT. I took this 2.303 from this side to right side. Then it will be minus EA by 2.303 RT. So if I rearrange or rewrite this equation, what it will be? Log K is equal to log A minus A by 2.303 RT. This is the very important equation. Okay. So if you plot the graph, same graph if you are plotting by taking log K on y-axis and 1 by T on the x-axis, what will be the slope you are getting? See here, what will be the slope we will be getting? It will be minus EA by 2.303. here if you are plotting log k versus 1 by t, we will be getting the slope that is equal to minus EA by 2.303 R, right? So, when the questions comes, you should clearly check that in the graph whether it is plotted natural log or log. Okay, then based on that your slope value will be, there will be slight variation, because in natural log once you convert into log will be 2.303 will be getting multiplied there, right? So I hope this is clear for you. Now another one important equation here is, so here what we got now, log k is equal to log a minus a by 2.303 RT, right? This is what the equation we got here. Log k is equal to log a minus EA by 2.303 RT. Now, if the reaction is taking place at two temperature and we are getting two rate constants, okay? The rate constant for first temperature T1, it is K1, and for the temperature T2, it is the rate constant is K2. Just substitute that values in equation, what we will get. Let's see, when the temperature T1 and rate constant K1, how we can write it? The first equation will be log K1 is equal to log A minus A by 2.303 or what is the temperature here? It is, temperature is T1, right? T1. Okay, take it as your first equation. Okay. So for the second one, rate constant 2, it will be, then it will be log K2 is equal to log A minus EA by 2.303 or what is the temperature? Is T2, right? Take it as the second equation, right? If you subtract the second equation from the first equation, or anyways you can do, you can subtract from second to 1 or first to second, okay? What we will be getting? Check. You are minusing the second equation, the first one. So what it will be? Then it will be log K2 minus log K1, right? In here side, this side, right side, what will happen? Log A minus log A. The term will be getting cancelled, right? Then it will be, second one is minus EA by 0.303 R. This will be constant there. Then it will be, what the value will be? 1 by T2. These two terms are common in the two equations, right? So we can take the EA by 2.303 as common. Then it will be 1 by T2 minus 1 by T1, right? So I can rearrange this equation as log K2 by K1 is K2 minus log K2 minus log K1. We can write it as log K2 by K1, isn't it? Equal to, taking this negative sign there, so it will be EA by 2.303 R into, what it will be? 1 by T1 minus by T2. Okay, I took this negative sign there, then it will be minus 1 by T2 plus 1 by T1, isn't it? That I can rearrange like this. 1 by T1 minus 1 by T2. Is that clear? Okay, so this is the very important equation that the questions for the problems it will be provided with the two rate constants K1 and K2, whether it may be given directly or indirectly. Okay, and it will be provided with the two temperatures in Kelvin scale, and you have to calculate the activation energy. There you have to use this equation, right? So log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. Again I am telling this is a very important equation. Definitely there will be problems coming from this session. Okay, so don't forget to learn this equation while going for the exams, right? So I hope this will be clear for you. Send it. Now we can see how the catalyst will affect the rate of a reaction. So what do you mean by this catalyst? Catalyst is nothing but a substance that will help to increase the rate of reaction by itself without undergoing any change. The catalyst won't undergo any permanent changes, but it will interfere in the reaction and thereby promote the or increases the rate of a reaction. Okay, so a catalyst is a substance which increases the rate of a reaction without itself undergoing any permanent chemical changes. The catalyst won't have any permanent chemical changes, but it will help to increase the rate of reaction. How it is possible? We can discuss it in detail in this session. Okay, so actually what a catalyst is doing is it will form an intermediate complex. The action of catalyst we can explain by intermediate complex theory. Let's see an example. Okay, you are taking an example of reactant A and B reacting in presence of X. Okay, these two are our reactants and this is our catalyst. Okay, now see what will happen is this catalyst will react with, or not reacting, it will form an intermediate complex with the reactant molecules. See, this will form A, E, it will form a temporary bond like this, the reacting molecule. This is what we called intermediate complex. This intermediate complex is unstable. It will be breaking down to give the product, and we can see the catalyst will be getting. Okay, that's what I told you. The catalyst is a substance which will help to increase the rate of reaction without itself undergoing any permanent change. Okay, so here you will ask that it only form an intermediate complex, then how the reaction rate is increasing, right? Catalyst will decrease the activation energy. Okay, what will happen if the activation energy get decreased? So more molecule will acquire the activation energy greater than or equal to the required energy, right? So more reactant molecule will be reacting in a faster way. So what will happen? The rate of the reaction will be getting increased, isn't it? So here see, the catalyst provides an alternate pathway for the reaction mechanism by reducing the activation energy. The term is the important one for getting the idea about effect of catalyst. The catalyst will reduce the required activation energy. Okay, so the catalyst provides an alternate pathway or an alternate mechanism for the reaction by reducing the activation energy of the reactant and the product. Okay, so thereby lowering the energy barrier, potential energy barrier. Here we have drawn a graph that between taking the potential energy on the y-axis and reaction coordinates on x-axis. We have already seen here this graph, the potential energy, reaction coordinate, the reactant molecules reacting to form the activated complex, right? Now let's see how the catalyst will affect that reaction. See, here what will happen is, this is what the potential energy of reactant molecule, they are forming the activated complex and the product is forming. This is what the curve we are obtaining when there is no catalyst involved in the reaction. Okay, so we can note it as without catalyst, right? This is the graph we are getting for a reaction that is proceeding in the absence of a catalyst. So here what we will get, this is the activation energy required for this process, right? The activation energy required for that process that is proceeding in the absence of a catalyst. Okay. Now let's see, if you are using a catalyst in this reaction, so see what will happen is, in the presence of catalyst we can see that the activation energy is getting boost. See, before in the absence of catalyst, this much of waste. See, in the absence of catalyst, this much of activation energy is needed. But in the presence of catalyst, see here how much activation energy is required? Only this much of activation energy is required. So, what the catalyst did in that? The catalyst reduced or decreased the activation energy required for the process, so that our molecule will be attaining energy equal to or greater than that of the activation energy. So, the reaction will proceed in a faster way. So, did you get an idea how the catalyst increases the rate of a reaction? That by reducing the activation energy of the reaction. Okay. So, now see certain characteristics of catalyst. This 5 points are very important one. See, the catalyst, if it is in a small amount also, it can catalyze a large number of reactant molecules. We don't need that much of reactant molecules. If you are taking a large number of reactant molecules, only a small amount of catalyst will be enough for or speed that reaction. Okay, it's not about the amount. A small amount of catalyst can also catalyze a large amount of, right? The next point is very important point, that is a catalyst do not alter the Gibbs energy of a reaction. Repeating, the catalyst do not alter, it will not make any changes in the Gibbs energy of the reaction. Okay. And the next point is, the catalyst catalyzes spontaneous reactions. Won't catalyze the non-spontaneous reactions. Okay. The catalyzes the spontaneous reactions. And the next point is, the catalyst does not change the equilibrium constant of the reaction. Rather than it will fastens, it will help to attain the equilibrium constant in a faster way, but it will not alter the equilibrium constant. Okay. Next one is, the catalyzes both forwarded as well as backwarded reaction, thereby help to maintain the equilibrium constant and reaching the equilibrium constant in a faster way. Okay. So, these are the main 5 characteristics of catalyst, that is, a small amount of catalyst is required for a large amount of reactant molecules, and A catalyst does not alter the Gibbs energy of a reaction, catalyzes the spontaneous reaction, and catalyst does not change the equilibrium constant of a reaction, and it catalyzes both the forwarded as well as the backwarded reactions and thereby help to attain the equilibrium or to maintain the equilibrium. Okay? I hope the effect of catalyst, what is a catalyst, and effect of catalyst and characteristics of catalyst is here for you. While learning the catalyst, you should know one more term, that is inhibitor. So what does this inhibitor means? Inhibitor means it will reduce the, okay, it will inhibit the reaction. Okay. Now let's see another term in this chapter, that is the collision theory of molecule. Okay. From the word itself we can learn what is the collision theory. According to collision theory, we will consider the reactant molecules as small spheres. Okay, small spherical structure. What will happen is the spherical structures will collide with each other. Okay, not all the collisions will lead to the formation of product. Only the effective collisions will lead to the formation of product. Then what is this effective collision? Discuss it later. And here see, the reactant molecules are assumed to be spheres and reaction occur when these molecules collide with each other. So whenever you see the collision theory, it should be there in your mind that it is about collision of reacting. Okay, there we will consider the reactant molecules as spherical structures. What will happen? Whenever these reactant molecules collides in an effective way, very effective way, if they are colliding, then only it will turn out to product. Okay. So, according to collision theory, the rate constant or the rate of reaction depending on one more factor, that is the collision frequency. Okay. What is this collision frequency? That if you consider a unit volume of reactant molecules, okay, we will be considering a unit volume of the reacting molecules. In that, within a second, how many collisions are taking place? That is what the collision frequency. See, the number of collisions per second per unit volume of the reaction mixture is what we call the collision frequency. We will consider a unit volume of reaction mixture, and within that, in second, how many collisions, the number of collisions per second per unit volume of reaction mixture is what we call the collision frequency. In the last compartment examination, there was a question that to define the collision frequency. So, remember that the collision frequency is the number of collisions per second per unit volume of what reaction is what we call the collision frequency, and we denote it with the letter Z. Okay. Now see, what is an effective collision? So according to collision theory, the collision of the reactant molecule is responsible for the formation of product, right? In that also, all the collisions will not lead to the formation of product. Only the effective collision will lead to the formation of product. Then what is effective collision? Effective collision means the colliding molecules should have an maximum energy. Effective energy should be there. Okay, the colliding molecules are colliding with a sufficient energy, and it's not merely about colliding with sufficient energy. That collision should be in a proper orientation. Then only we can say it is an effective collision. That means the colliding molecule should have a sufficient energy as well as they are colliding in a proper orientation, in a proper direction. then only it will form an effective collision. If there is effective collision only, the reactant will react to give the product. Okay, so effective collision is clear, right? The collisions in which the molecules collide with sufficient kinetic energy and proper orientation, then only there will be breaking of bonds between the reacting species and the formation of new bonds in the product will take place. That is what we called effective collision. So remember that effective collision means with sufficient kinetic energy plus proper orientation in proper direction. Then only if the collision is taking place on basis of these two factors only, it will lead to formation of product, that by breaking the bonds in the reactants and forming the new bonds in the product. Okay. So I hope effective collision is clear for you. Now see, in collision theory, the activation energy and proper orientation of molecule together determine the effective collision. So according to collision theory, how we can write the rate constant is K is equal to P into Z, any reacting molecules. If we are taking A and B as the reacting molecule, ZAB. What is Z? It is collision frequency in terms of reactant molecule. Okay. So E raised to minus EA by RT. So according to collision theory, the rate constant K is equal to, what is this P? P is the steric factor, that is the proper orientation. What is orientation? I will explain it with an example. See, here we are taking the reaction CH3Br reacting with OH minus, and we have to get 3OH methanol plus Br minus, right? I can write this reaction two ways, with proper orientation as well as in improper orientation. See, here CH3Br, right, reacting with OH minus. Let's see if it is taking place in this way, right? CH3, we can write it as 3 hydrogen molecules, right? 3 hydrogen atoms. Write it as H, H, H. That is what the CH3. Okay. And here bromine was there. So this bromine will have a slight negative charge, right? Carbon will have a slight positive charge. See, if the OH molecule is coming in this direction, in this orientation, what will happen? OH minus, see, if it is forming a, write a bond there. Okay, see, if it is forming a small bond here, will there a bond formation occur? No, right? There won't be any bond formation because these two are negatively charged. This is what we call the improper orientation. See, in improper orientation, whether there will be product, there will be no product. Isn't it? Now let's see. If this OH is coming like this, this is the carbon with the 3 hydrogen atom, and if the OH is coming in this way, the slight negative, positive, so OH can attach here. See, this is what we call the proper orientation. If it is coming in a proper direction, then only here what will happen? This bond will be taking, what we will get? 3H plus Br minus. when the molecules are colliding in the proper orientation, then only the product will be forming there. Okay, that orientation is what we given by the letter P. Okay, and ZAB we already discussed. This is the collision frequency. Okay, and these all terms we are familiar now. That is, EA is the activation energy, R is the gas constant, and T is the temperature. Okay, so according to collision theory, this is the equation that relates the rate constant and the proper orientation and collision frequency as well as activation energy, gas constant and temperature. Okay, that clear? Okay, now let's see one question from the topic that we covered now. Okay, so what will be the effect of adding a catalyst on activation energy? What is the effect? How the catalyst is acting? It will increase the activation energy, right? That is how the catalyst speed up the reaction rate, isn't it? So, what is the effect of adding a catalyst on activation energy? It will reduce the activation energy, right? So, what about the second question? What will be the effect of adding catalyst on Gibbs energy of reaction? Will the catalyst alter the Gibbs energy? No, right? There won't be any effect on the Gibbs energy of reaction. We have clearly mentioned in the characteristics of catalyst that a catalyst will not alter the Gibbs energy of a reaction. Okay? So, if the questions are coming like this, you should be able to write it in with a proper explanation. It is asking for 3 marks question, right? Okay, now let's see one more important question. That is, a first order reaction is 50% completed in 30 minutes at 300 Kelvin temperature, and it completed in 10 minutes at 320 Kelvin. Want to calculate the activation energy of reaction. By learning the Arrhenius equation, I have mentioned you that this kind of questions you can expect for the problems, right? See here what it is given. Reactions, 50% of reaction is completed. That means 50% means the half-life, right? So what it is given in the question? It is the half-life of reaction. Here two temperatures are given, right? We can take it as T1 and T2. Okay, which value is T1? It is, we can take it as 300 Kelvin. 300 Kelvin is your first temperature. It is capital letter K, right? Temperature, Kelvin. And T2 is 320 Kelvin, right? So, what is given here? This is clearly mentioned that it is a first order reaction and it's 50% completed means it is the half-life of reaction. What is the equation for finding out the half-life of first order reaction? It is T half is equal to, for first order reaction, it is 0.693 divided by K, right? It is given its value, T half is given in question as 30 minutes, isn't it? So, we can easily find the K1 there. It will be, this is T1 for temperature. T1, it is 30 minutes, right? So, this will be K1 is equal to what? 0.693 divided by what? 30, right? So, how we can write it? Will be 0.3231, right? Okay, 0.231 divided by 10, right? You can rewrite equation as 0.1 by 10, that is 0.0231. 31, what is the unit? Minute inverse. That will be your K1 value. Same way we can find out the K2 also. It's given at 320 minutes. The half-life is 10 minutes. Then it will be, how will be the K2 value? It is equal to 0.693 by, 693 by, what is the half-life there? 10 minutes, right? Then it will be 0.0693 inverse. Now we got the T1, T2, K1 and K2. You can easily find out what the activation energy by using which equation? That is log K2 by K1 is equal to EA by 2.303 into 1 by 1 minus 1 by 2, right? So when substituting the values, what we will getting will be log, what is the value for K2? Plus 0.0693 divided by value for K1, it is 0.0231 is equal to EA by 0.303 into 1 by T1 is 100. 1 by 300 minus 1 by 320. Isn't it? So 0.0693 divided by 0.023, it will be 693 divided by 231. That is 3, right? 231 into 3. 693. So, here this value will be log 3 is equal to EA by 2.303 into 1 by 300 minus 1 by 320. Cross multiplication, we will get 320 minus 300. That is 20 divided by 300 into 320. Right? So, forget the gas constant R, isn't it? The equation is log K2 by K1 EA by 2.303 R into 1 by T1 minus 1 by T2. Okay. So, when substituting the value for log 3 is 0.4771 equal to EA by 2.3 into, what is the value of gas constant? 8.314 into, it will be 10 1 by 30 right to 1. So, multiply, when you take this all on this side, then it will be 0.4771 into 2.303 into 8.314 into 300 into 160. That will be the value for activation energy. EA is equal to 0.4771 into 2.303 into 8.314 into 300 into 30 into 160. Okay, when you multiply all this, you will get the value for activation energy, and what will be its unit? It will be joule per mole. Okay, or you can convert it into kilojoule. Okay, this is the way to solve this equation. The same type of question, that is the rate of a particular reaction quadruples on increasing the temperature from 293 to 313 Kelvin. Okay, so here the temperature it is given T1 293 Kelvin and the T2 is 313 Kelvin. Okay, so what it is given, instead of giving directly the K1 and K2 value, here the rate constant, first rate constant we can take it as K1. K1 we can take as K, and the reaction quadruples. Quadruples means it increased by 4 times. So, your K2 value will be, what? Quadruples means it will be 4K, right? Then directly by substituting in the equation, that is log K2 means 4K by K equal to K by 2.303 into 8.314 to what will come? 1 by T1 is 293 minus 1 by T2 is 13. Okay. Here you will get the value for log 4 and by doing the same problem, same way what we did for the previous question. Okay, we can solve this question. You can expect this kind of questions for your board exams. The rate constant may not be given directly, it will be given like this, quadruples or double the rate constant when you increase the temperature from this Kelvin to this much Kelvin to that much. Or it will be giving like in the previous question, like giving the half-life of the reaction, and from that you have to find out the rate constant. Okay. So, these are the main things in this particular chapter. So, whatever the things we covered in this chemical kinetics chapter is, I have discussed about the rate of the reaction, the different factors that affect the rate of reaction, and the rate law, the very important one, that is rate is equal to rate constant K into concentration of reactant molecules, which each term raised to some power that may or may not be the stoichiometric coefficient, right? And we have find out some trick for calculating the unit of rate constant, that is mole inverse, mole raised to 1 minus n, liter raised to n minus 1 and second inverse. Okay, then what is the order of reaction? It is the sum of those exponents in the rate law equation. And what about the molecularity of reaction? The number of molecules that involved in a or actively participating in a chemical reaction is what we call the molecularity. And if you get the order, we can easily find out the unit of rate constant. That all these things we have discussed detail in the first and second part of the videos, right? And also the integrated rate equations for zero order, what we learned? Zero order, the rate constant K is equal to R0, initial concentration of reactant minus final concentration of reactant divided by time taken, and the half-life of zero order reaction is given by, it is directly proportional to initial concentration of reactant divided by 2K. Okay, and for the first order reaction, the rate constant K is given by 2.303 by T log concentration of reactant at 0 time divided by concentration of reactant at T time, and the T half-life is given by independent of the concentration of reactant. Okay, and the activation energy, Arrhenius equation, concept of collision theory, that all things we have discussed today. Okay, so with this I am winding up the session today, and I will be coming with a new chapter from your grade 12 chemistry. And one more thing is, your Satin sir will be coming for live on the coming Wednesday, that is 4th October, with the applications of derivatives. So don't miss that class. Stay tuned with us. Thank you.